Hey, what's going on, guys? GoMegaGames here. Finally, I got the very first successful results regarding Texel's tuning being applied to my JavaScript chess engine Wukong. So I've currently ran 2 stages. So the very first stage was a match versus the very first initial version 1.1, which had the simplified evaluation by Tomasz Michniewski, not against the tables from Ronald Frederick, but instead by those a very simplified evaluation. Just to give you an idea of what am I talking about. I'm sorry for this always on top windows, otherwise I'm just losing them, so it's not really that great idea. So if we just go for simplified evaluation, so just to give you an idea of what kind of the values were participating within this tournaments. So this sort of values are very well-known ones were used as the basis. So only this values, no tapered evaluation was actually used within my version 1.1. Well, I've used the starting rate in 1700s, while WukongJS 1.1 is actually around maybe 1600s. So it's not an absolute rating. It's the relative rating. So it's kind of like for about plus 27. Well, obviously we have there is an error, the possible like plus minus. I'm not sure how to calculate that. So it might be a bit greater, a bit less, but just a very rough estimate we can see is that this kind of version with it after the very first Texel's tuning has been applied to the positional square tables and material weights, I get these results. I'll not cover in great details what steps did I make in particular and how in particular the theory that been described in the previous video was actually applied to tune WukongJS. So that's just about to come just right in a moment. And here this is the recent match. Well, so here I have 500 games, so it's the error is really less than right over in here. But again, like I've just dropped this one because it had this error for like the rating wasn't really changing much. So probably I could have run a bit more games, but just with this 168 games, and I just dropped that because the advantage was already staying quite pretty nicely. So we have 47 elo advantage. So this the stage 2 of tuning is 47 elo points better compared to this one that is on its own 27 for about around rough estimate 27 elo points stronger than the bare p-square tables. So eventually I've managed to gain, so I'm very bad at calculating things in my head, so let's say 27 plus 47. Okay, so it's around 74 elo points, which is really not that bad at all, especially when you will realize how in particular I was actually tuning this. And when you will realize how in particular I was doing this, you will be very surprised by these values because they are quite pretty impressive, basically. So this is it regarding the current stage. Yeah, what else? So now, yeah, I have all of I have these games, and I'll post the games, the links to the games in the description below the video, so you would be able to run this either within Arena or your own tool to calculate elo rating from the PGN file, just to reproduce the steps I've been doing here. But anyway, yeah, let me just, so as far as it's kind of quite pretty clear regarding the results, I just want to close the Arena. And now let's go to I just want to show you guys what kind of p-square tables and material weights I came up with so far using the Texel's tuning here. So temporary weights, I guess this version was, yeah, this version was how many was there? 27. Yeah, 27 elo points stronger compared to the version with bare this sort of values. And now how did I obtain this? Well, I've been trying different approaches. So you've seen like I've been using 500 games there, and I was trying to learn like to tune the weights based on the games from gm2600s.pgn file and from the position extracted from that file. And also I've tried to tune from the game set that has been extracted by self-play. And what I want to say that the mean square error was significantly less in case of GM2600s because, well, most likely because the win or lose was more or less like not a random, was less arbitrary in the GM2600s instead of my self-play, because assuming the very kind of short time control, only 100 milliseconds per move, it's kind of, so sometimes it might happen that you have a winning position but then something goes wrong, like some processing works in your computer, and this is the unfortunate situation where the engine that is currently about to move doesn't have enough processing power. It just returns a move from to the 2 place less than its opponent just done, and it results to blundering a queen or losing by the checkmate or whatever, or not finding the winning sequence otherwise. So I mean, like, the results from the self-play I've been using were not really that accurate. I tried both the datasets for tuning, but for me personally, this GM2600s, which I've been introducing in the previous video describing how in general Texel's tuning is actually working. So in that case, so those values, those positions being extracted worked much better, and eventually the values I came up with so far are used from those particular GM2600s positions being extracted from the PGN file. Now the very dramatic thing, and probably nobody was actually doing this, well, at very least it seems absolutely dumb, well, in my code Kicking style at very least. So yeah, so here is well, okay, probably before describing how in particular I came up with these tables, I just want to show 2 versions. I don't really remember where is the, so probably this is the second version, not sure really. Just need to check that out within my engine. So which one did I use eventually? So the one that has 5901 and 7061. Yeah, this is it, I guess, right? Yeah. So these 2 weights, okay. So this is the stage 1 tuning, and this is the stage 2 tuning. And you see, like, the difference in the numbers is quite pretty significant, but a very interesting thing that the most result I came up with wasn't actually done directly to the Texel's tuning, but due to a little trick by Kicking that I'm about to expose into public just right in a few moments. So what else did I want to mention here? Okay, so as you can probably see, it's quite pretty trivial to see that the values, well, first of all, I'm using the tapered interpolation, like, tapered evaluation and interpolating values between the opening and the end game has been described before. But what's new here? So you can see that I've used this simplified evaluation by Tomasz Michniewski as the initial pattern to work with, and then I was applying Texel's tuning to it. But you can see that it doesn't actually assume tapered evaluation. Instead, it has only endgame values for a king. Well, it doesn't have endgame values for whatever other p-squared tables but king. And when I wasn't before implementing the Texel's tuning and applying this to my engine, I was trying to handcraft the endgame values for this p-squared table, endgame values for pawns, knights, etc. So, but whatever I tried resulted in a much worse play compared to the original version that didn't actually even use the tapered evaluation, believe it or not. So the very first achievement I got was actually to provide such a particular endgame p-square table weights, so that the version with a tapered evaluation at very least doesn't lose to the initial version without tapered evaluation, which was a little bit of a challenge to come up with, to solve basically. And then I started. So let's just go step by step. So the very first trick, I don't know, maybe people, well, obviously, I believe if you think that you have invented something, that probably just don't know the original creator of the method that you're kind of thinking you have invented. But so what I was trying to do, assuming the fact that I actually have a very, very slow implementation of the Texel tuning, and just to give you an idea of how many games I used in order to actually tune this stuff. So I was using in the range, so the maximal number I used was 30,000 games, and this was not for automated process. Well, I tried this as well, but just a few words about this later. But mainly regarding the automated stuff, I used only 1,000 games, believe it or not. So that might seem a little bit ridiculously small number, but you're just seeing the results. So let me just try and explain how on earth is this actually possible. So bearing in mind that the entire Texel tuning error is just a matter of minimizing the mean square error for all the weights we're about to tune, I decided that the more accurate values I would provide initially to apply this tuning routine for, the better it would result eventually. Because I just realized that I could have, so let's just have a look at the initial weights. So probably, yeah. So here is the well, it's actually not the most initial weights. Yeah, it's already after a couple of stages, apparently non-successful ones. Okay, what about this initial weights? Yeah, so just want to show you this little example. So you just have a look at the pawn table of the pawn table of simplified evaluation by Tomasz Michniewski. So you see, well, the very first thing that you can see that the values are symmetrical. That's the first thing. And the second thing, that no matter which pawn to promote here, so literally it says like all the pawns on the 7th rank has the equal score. While on the real deal, non-symmetrical values, as mentioned by Ronald Friedrich, by the way, are working much better. So eventually, well, this weight's not really representing this much. It's just a slight difference between the weights, and this didn't really. So this did result only around 27 elo points breakthrough. Not much really, but these values. So I was just manipulating the values and recalculating the mean square error for 30,000 positions. So it takes quite a bit of time, but if you just change several parameters by hand and see whether the mean square error is getting reduced or not, it's not really that long. So what I managed to do so far, I was trying to make this table asymmetrical and give more bonuses to emphasize the queen side pawn, trying to promote faster. So, and this has minimized the initial mean square error I had before actually running the Texel tuning routine. So that's the core thing to consider. Also, we have a look, if we have a look at this pawn table for endgame, see, like I've dropped the board edge values, so they're back to 0, which also minimizes the mean square error for me. So the idea is very simple, just to give you an idea. So if I just comment this out and, well, let's say I just try to print this mean square error, let me just open terminal and say, okay, let's just run this. So Python 3 eval-tuner.py. Okay, so here I'm calculating the mean square error based on 30,000 positions from GM 2600 PGN positions that has been extracted. I just don't understand a little bit what's... Yeah, it's probably because my video recording software is working. It's kind of much slower. Okay? It's for about twice slower. So here is the error, and then this is kind of the manual representation of what happens automatically when the Texel tuning routine is running on the computer. So what it does is just adjust the values, recalculates, adjust the values, recalculates. So I thought, what if I just try to adjust the values by hands and then try to recalculate the error? So just to give you an idea, so let's say we have this value. So if now I say make this to 0 like this, it should be kind of worse, and the mean square error should get raised here because I've just dropped this kind of important 7th rank value. So let's just compare. So this now the mean square error should be maximized and increased, not reduced, because this kind of generally it's worse because we're not about to promote this sort of a point, or maybe it would be even better seen with this sort of a value. Yeah, so it's not significantly. Oh, hold on, did it just get minimized? Oh man, did it just get minimized? Well, in this case it did get minimized, but the matter of minimizing the mean square error doesn't always mean that you actually that it is actually better. So well, let me just try to make this back to 50 like this. At least now it should get increased, I hope, because yeah, this is a little bit weird. And again, like this is one of a very good examples of that if you just have the last mean square error, it doesn't obviously mean that it will be plain stronger, because okay, yeah, now it's, you see, like it has been increased. So we had 10 and all the stuff, now we have 89. So that mean square error has been increased. So let's say I had this sort of a this sort of input weights, and I've just changed this 50 to 170 because it just kind of quite often it happens that promoting pawns on the queen side results more actual queening within the game. So let's say I had this sort of a value, right? And now I've changed the value. I could have changed a couple of values, or 3 or up to 5 values at the same time. So it depends on the circumstances of what particularly you're trying to tune at the moment. But just simply changing this value, we can see like how the mean square error is going to reduce, and now we should get this value back because we've just increased slightly, well, from the statistical perspective at very least. Just hold on a sec, what the heck is that? Oh, it just dropped back to this one. Yeah, drop back. So this was probably, yeah, this was with a 0 instead of 70. Well, anyway, so this is kind of it basically. This is kind of it. And also, please know that even the material weights, now here in particular we have, the input weights has the same material weights, but after applying the automatic routine, they might be slightly different. They might have slightly different values, like white piece might be a couple of points be more expensive compared to the black piece, and on the contrary, but eventually this results in stronger play, believe it or not. So this asymmetrical weights within the pieces is also on the cards at some point. So just to give you an idea that I've changed the initial values of this simplified evaluation values, and just to make sure that the changes that I'm making would in theory be making some sense, I did make sure that at very least I'm not maximizing the mean square error after this sort of a changes. So what I want to say that even if you're not about to be running the Texel tuning in general, you can simply run a very simple function to calculate the mean square error from this is the entire method, not much here. So just run the routine. Just write the routine that calculates the mean square error based on the set of the given positions, and that's already kind of better compared to blindly changing the values and hoping for the best. Because you know, you may think like, okay, I just want to make it 90, 90, 100s, and this means like the pawns are about to be promoting there, but it's not always the case, and in the real game it might turn out as much weaker play. So that's something that I had. That's the trouble I got into numerous times during the development progress, basically. And when I've manually tuned all these values, well, at least those of the values that kind of seems to be reasonable from the human perspective, we have a look at this to make sure that the mean square error is not getting increased. Well, in my case, it has been reduced a little bit. And then I ran the actual Texel student routine, but not really that much to kind of like make it stronger, but rather to smoothen the values. So this is the core difference between the way how the Texel tuning was actually used by much better programmers than I am, including Ronald Friedrich apparently. I'm not sure regarding the details, but most likely. So they were using this Texel tuning with a not 1,000 or 30,000 positions like I did here. So I used 30,000 for manual tuning that I've just shown you here, and I've also used only 1,000 positions for automated tuning, which is very miserable, but quite pretty interesting thing that the mean square error within 1,030,000 is not really that different. It's slightly bigger within 1,000 compared to 30,000, but you know, like the direction of where in particular the values are about to be adjusted, I mean, like to the plausible or to the direction or to the negative direction instead, it remains the same regardless of whether we use this 30,000 or 1,000. Well, at least in my case, this was like this, like so. So I decided, so as far as the overall direction is the same, I can use just the last number of games to speed up the process, because with this value, it goes, it iterates over all the parameters, 794 to be exact, over, I don't know, about 10 hours maybe. So it's quite pretty long. So I was going to sleep, leaving my computer, calculating this stuff, and then in the morning I woke up, got only values that has been changed by 2 at very most, and the most difference was about like kind of 4 if plus 2 and minus 2, so it's kind of the delta was no more than 4 in this session weights here. But anyway, so that was kind of too long, and I tried this with the self-play games, and this resulted actually worse results, much worse results. So I dropped that completely and just dropped back to using the supervised learning, not reinforcement one, using the GM 2600s positions extracted from that PGN file, and dropping back to only 1,000. And then here you see like there were quite a few sessions. So with the 1,000 sessions, all of these guys, so it's around 10 of them, they were going for about, I don't know, maybe 3 hours. So it's much faster. So you just compare like 10 hours for 2 rows and like 3 hours for 10 or even 12 rows here. So it's quite pretty significant. And the values within this 1,000 was actually much better. They are those values that I've shown you in the very beginning of this video. So now the reason for actually, you might wonder then why on earth did I actually run this automated routine, if it might seem to be quite pretty enough to just to leave this initial weights like they are, but you just notice that I've made only pawns asymmetric in the opening and in the end game, while all the rest of the tables were not actually made asymmetric. So and again, like I was trying to play games like 2 sessions. So these are the initial 2 sessions, and starting from here we have a new training set. So I was trying this version, which was 2 loops over all the parameters. So the delta of the values was no more than 4. And also I tried to play this version versus this version where it was like 1, 2, 3, 4, 10. So it's about, well, okay, so just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So, and here the delta was could have been 20, because at very most plus 10 to a given value, at very least minus 10 to a value. So the difference, the biggest difference could be 20, right? Yeah. I mean, like not for a single given value, but I mean the delta between two different values. So let's say this was 10 and this was 10. So this becomes 20 and this becomes 0. So we have plus 10 here and minus 10 here. In this case we have 20 here and 0 here. So the delta between these two values would be 20. That's what I mean basically. And this version performs even worse than the initial version without tapered evaluation, the pure p-squared table. So what I've realized that only around the second run, with only this 1,000 games to calculate the mean square error for, actually results like with the best results. That's the trial and error method by CodeMac I came up with so far. So you've just seen the results. So I'm now about to run the. I'm about to run a new match versus TSCP to see how probably worse it would be compared to the p-squared table values by Ronald Friedrich. So that's kind of it basically. And yeah, so this is kind of it. Also a very quick update. The new version is about to be released quite pretty soon, and I would make an extended video on what in particular and how exactly has been changed. But just a very quick overview, because I'm really tempted to share this stuff with you guys. So if we have a look, so first I've implemented the opening book, so we can it's now randomizing the moves. So you can, it's not only to this, to really, it's about eight lines here. I've handcrafted all the lines on my own. So just to give you an idea how this kind of looks, how this works, you've just seen how this looks like. So here, it's only the feature for plain browser mode. It's only for the browser mode. So here I have a book. I have Wukong.js file, which you can easily extend or change on your own. So you just need to use this UCI format for move sequence, and every next element within this book list is a new line, and it randomly picks whatever from this line. So we have 3 lines for E2, starting with the E2, E4, 2 Sicilian defenses, 1 closed, 1 dragon. I'm not sure which one is closed. So this is the closed, this is the dragon, G7, G6, right? Okay, just hold on a sec, man. I'm about to help, just run in a moment. So Sicilian closed, Sicilian dragon, and this one is a real pass martial attack, believe it or not. This one is G2, G3. I'm not sure. Oh, it's transposed into the English Open, if I'm not mistaken. This is a sort of a Slav defense, or well, might be wrong in the opening name, but just D4, D7, D2, D4, D7, D5, C2, C4, C7, C6. So this is the Slav defense, if I'm not mistaken, and the English opening at the very end. So again, like, feel free to adjust this. Yeah. Also, these 2 openings are one of my favorite openings. I like to play in Blitz. I didn't play in chess and Blitz for a very long time. The very last time was probably when I was playing versus one of my subscribers. He was also a chess engine developer. Okay, so again, like just to give you an idea, so this is the opening book to be manipulated. So just feel free to play around with this, and then you just can play the moves. And so now it goes for Sicilian Dragons. So as long as you follow the theory here, it doesn't cover all the theoretical lines. Yeah, so now you see, like, already drops. So it's no longer a theoretical line here. So just try to exchange the bishops here. It's probably no longer possible even. No, fortunately, the computer doesn't know about the h-file attack. Doesn't know anything about that h-file attack. And I can now try to checkmate this guy. Okay. Oh, just lost all of my pawns. Do I still have a chance? do I still have a chance here? Oh man, no. Well, forget that. So it should be quite pretty easy to outplay this this computer in Sicilian Dragon if you know the theory and the particular order of moves. Same for the rest of the openings. So I've also added one of my favorite openings to play. So this is it. Yeah, it's probably the opening line has just changed. So as far as the opening line changes, it starts printing the book move. It just starts printing the score and the principal variation that engine has calculated. So I hope this is quite pretty clear. And another quite pretty important improvement is that finally I've added the transposition table, and it actually searches around 2 places deeper in a middle game, well, as well as in the opening. So it was like 6, 7, and now it's about 7, 8, and sometimes 9. Closer to the end game, it goes 10, even 13 from time to time. In the deep end game goes even further. So the browser version uses the default 16 megabytes transposition table. So just to give you a very quick idea. Oh no, it's not here. I just want to show you this UCI part. Yeah, so in UCI you can set up the hash just using the standard UCI command for that. Also, this should also can be done. Well, I was testing this with the Arena GUI, so whatever other GUI should be working as well. So you just can manually set up the number of megabytes to use for a hash table. And one last thing, that if you still don't really want to get your hands dirty with this UCI stuff and running the script as a backend, installing Node.js and all this stuff, and if you just want to try to change the size of transposition table just directly in the browser, this is also possible, and this is the way how it is possible. So here in the API, well, it's probably better to show you this right over in here. So I've added a new method to the public API of WukongJS. So let's go to the API docs here, and now it's in the very bottom here we have this set hash table size. So we can simply say engine set hash size, and then the number of and then kind of what kind of value do we want to have there. So this is my local one. Well, I can even show you this within by the way, I'm just wondering, did I already git push the latest changes with the opening book? I'm just really wondering. So just let me try. Yeah, I already did. So if you just open the terminal, the Chrome browser developer tools, or in Firefox, this is the same, and I just say engine dot set hash size, and yeah, let's try 64. So you see it sets the hash to 64. The hash table has been initialized with this sort of a number of entries. Then let's say try to drop back to 16 megabytes, so it's already last entries. If you try the values below the bottom margin, it would automatically set to the 4 megabytes, which is the minimal size for a hash table. If you try to exceed the upper margin, it will set to the most upper margin being available. And again, like by default, it always starts with the 16. And in Arena GUI, the default is 64 megabytes, but that is getting set automatically by the Arena GUI itself, so no worries regarding that. So this might be only interesting to testers who's setting up the hashes when running matches like one engine versus another. Well, okay guys, so I think this is it from my side. New version is about to come quite pretty soon. I just need to run quite a bit of more tests at the moment, so just to make sure everything is working properly. And I'm already very close to the stage where I will ask Gaber Schatz, the guy from CCRL who is actually testing this chess engine, to get an official rating, the very first official rating for WukongJS. This would be the version 1.4, and we'll see how the rating I think it has would be correlating with the actual rating that it will get after testing versus really lots of other engines, not only TSCP but other engines as well. So this is it from my side. Feel free to play around with these new updated features of WukongJS. Hope to see you next time. Until then, and take care.